Hi, this is a lecture series for chemical engineering thermodynamics, and at this point we are at lecture 3B. Just for the recap, for lecture 3A, I mentioned about behavior regarding relationship between three variables: pressure, temperature, and volume. And in lecture 3A, I show you the diagram and describe about behavior under different region in the diagram. For this lecture, we will convert the diagram into equations so that we can apply that equation in the calculation regarding first law and other aspect in thermodynamics. Let's start with equation of state. The meaning of equation of state is basically the relationship between temperature, pressure, and volume of fluid. It was originally derived for gas and vapor, and the very first one that everybody already knew would be ideal gas law, which was derived from the combination of Boyle's law and Charles' law. But in this course, we will take that everybody already know about this ideal gas law. Then we will try to modify the ideal gas law. Modification can be categorized into two groups. The first group is basically using a correction factor. In this case, it is what we call compressibility factor. The second way to modify the ideal gas law is basically changing the form of the equation itself. Let me go into a little bit of the detail. For the first one, the use of compressibility factor. Originally, ideal gas law is PV equal to RT. If we introduce another factor called Z, or compressibility factor, this variable can be used as a correction factor to make the equation fit the experimental data or real behavior much better. But the Z itself is not a constant. It can be derived or found by various ways. For instance, the most basic one would be the chart. You can read out the value of Z at various conditions from the chart called Z chart. Or you can calculate Z using another set of equations, for instance, Var equations. Or another set of equations that can be used to calculate Z is also a Pitzer correlation. These two equations will be covered in the second part of lecture 3B. Then, for the second kind of modification of the ideal gas law is basically changing the form of the equation. Originally, ideal gas law is in this form, but some scientists noticed that if he or she modified the form of the equation to make it more complicated, the equation like this would have higher capability to fit the experimental data much better. And there are so many forms of equation that can be learned, but the most common group of equation of state is what we call cubic equation of state. And the content regarding cubic equation of state will be covered in the third part of lecture 3B. Recently, these two modification of ideal gas law, even though originally it was derived to fit experimental data for gas, but later on it can be adapted so that properties of liquid can also be described using these two equations. Some equations can even describe relationship between vapor and liquid at equilibrium. We will talk about that in more detail. For this part of lecture 3B, for the first part, we will spend time talking about ideal gas law mostly. It is written in the form of PV equal RT, as everybody already knew. In this case, I like to emphasize that this V is molar volume. Some of you may be familiar with another form of ideal gas law, PV equal to nRT. In that case, N is number of moles. Therefore, the V in that equation would be the total volume. Ideal gas law was derived fundamentally based on two assumptions. The first one is that molecules do not occupy space. What does it mean? If you have a gas within a container, okay? If I make some kind of exaggeration, let me put molecules as dots here. The volume that corresponds to change in temperature and pressure should be the volume highlighted in white in this picture. So it is the white volume there that will be changed when you change temperature and pressure of your system. The volume occupied by the molecule itself does not change with respect to pressure and temperature at all. So in the ideal gas law, it is assumed that atoms or molecules do not occupy any space. The space between molecules is therefore equal to the volume of the container. Okay, so in this case, the volume that we use is the whole volume of the system, and therefore you have to make sure, or you have to realize that theoretically the volume that we have to calculate or we have to put into the relationship is indeed intermolecular volume. But for ideal gas law, since we assume that molecular volume itself has no volume, so in this case intermolecular volume would be equal to system volume. The second assumption for ideal gas law is that among molecules there is no interaction. Okay? In general, molecules is consisted of atoms, and within atoms you have protons and electrons. Protons from one atom can attract electrons from others. So atoms further apart may have attraction in some sort. On the other hand, if two atoms come closer together, repulsion between electrons from two atoms may also take place, especially when the distance between two atoms are relatively close, or when we have higher pressure. So that means when you change pressure, the real interaction between atoms would change, would be a function of pressure. But in ideal gas law neglect such interaction. It is also complies with the first assumption that molecules does not occupy any space. So there's no molecule basically, and there's no interaction among molecules. If you recall lecture 1a, I mentioned that internal energy depends on three factors: temperature, phase of the fluid, and chemical composition or bonding within the fluid itself. If we apply these three factors to ideal gas law, then you should notice that since we said it is gas, for ideal gas it is applicable only for gas. So the phase here is already explicitly described as gas. Okay? So doesn't matter what kind of gas you are considered, as long as it is assumed to be ideal gas, the phase here is fixed. On the other hand, if we assume the gas to behave as ideal gas, there is no intermolecular interaction amongst molecules. So it doesn't matter what kind of molecules you have. Even though you have water, which can have very strong attraction amongst molecules, or you have argon, which has almost no interaction at all, it does not change the fact that ideal gas law assumes no interaction. So chemical composition here doesn't matter anymore in the case of ideal gas law, such that for ideal gas, the internal energy would be a function of temperature only. Okay, so this is the very important consequence of these two assumptions. So you have to memorize that whenever you assume gas to be ideal gas, the internal energy of your gas now is function of temperature only. So if we recall from lecture 3 or lecture 2a, for gas, for one component gas, one phase, one component, degree of freedom is 2. So if I want to express internal energy as a function of two variables, those two variables are usually temperature and volume. According to calculus, we can expand the differentiation of internal energy into two terms. The first term is called CV here. The change in internal energy with respect to temperature at constant volume is defined as CV. And then the next term, I told you that this could be derived using the equation in lecture 5a to end up with this equation. For ideal gas, I show you in lecture 2b or 2a that when you plug in relationship of ideal gas law into this derivative, the whole term would become 0. Okay? So during that time, I also confirmed that for ideal gas, the internal energy is a function of temperature only. On the other hand, if you start from saying that internal energy is function of temperature only from the discussion of these two assumptions, then we can say that internal energy is function of only one variable, temperature here. If you take derivative, du now will equal to cv dt. Why I can say that? Because according to the definition, cv is du by dt. But since internal energy of ideal gas is a function of temperature only, then you don't need partial differentiation anymore. Now the derivative can be written in terms of total derivative. When you rearrange the equation, you end up with du equal to cv dt like this. So it doesn't matter whether you write it from generic equation or using ideal gas assumption, you end up in similar manner. But to be clear, in this case, I like to put superscript ig here to just identify that this heat capacity is a heat capacity at the state of ideal gas. By definition, heat capacity is still differentiation of internal energy with respect to temperature at constant volume. But in this case, since internal energy is a function of temperature only, the right-hand side of this equation would be a function of temperature only. So therefore, heat capacity of ideal gas would be a function of temperature only. If we start from definition of enthalpy, then applying ideal gas law to PV term, the PV would equal to RT. Now you can realize that U is a function of temperature only, and we have T here and R is constant. Therefore, the right-hand side is a function of temperature only. That means for ideal gas, enthalpy is a function of temperature only. And from definition of heat capacity Cp is differentiation of enthalpy with respect to temperature. Now if enthalpy is a function of temperature only, differentiation here can be written as total differentiation, and we can say that heat capacity Cp of ideal gas is also a function of temperature only. When you combine this, or if you rearrange this equation, you get dH equal to Cp dt. Just in the similar manner as what we derived earlier in lecture 2a. Lastly, from this equation, if you take derivative with respect to temperature, this temperature here would be differentiated to get dt by dt, which is 1. Okay, dH by dt, from this equation you end up with Cp, while du by dt here you end up from this equation to be Cv. So at the end you obtain the relationship between Cv and Cp for ideal gas to be this equation. And please note that this equation was derived only for ideal gas, so therefore it is invalid for non-ideal gas or other kind of fluid. The assumption that I mentioned earlier is applicable only when atoms or molecules are further apart. If you consider it closely, the volume of atoms or molecules will be negligible only when the total volume of the system is very far, very large comparing to the size of atom itself. For the second assumption, it will be true only when atoms are further apart, or atoms are moving at very high velocity. Okay, such condition can take place only when pressure is low and temperature is high. The question would be how low the temperature should be so that the ideal gas assumption is applicable, and how high the temperature should be. In general, the rule of thumb would say temperature should be higher than 0 degrees Celsius, and pressure should be low enough in the range of 1 or 2 atm. But it doesn't mean that if you have pressure higher than that, for instance 2.5 atm, it doesn't mean that at that pressure ideal gas law is not applicable. It is still usable, but you have to realize that there will be some error associated with it. And this error will grow larger and larger as you increase the pressure to higher value. Next would be the examples how we can use ideal gas in several cases. The first case would be the process undergoes isochloric or constant volume. For generic fluid, as long as it is gas or single phase, single components, degree of freedom is 2, then you can use this equation, and the first term becomes Cv, the second term becomes these groups. Okay, if the volume is constant, then dV becomes 0, and then you will end up with du equal to Cv dt. Okay, on the other hand, for ideal gas, we know that internal energy is a function of temperature only for ideal gas. If you take derivative, you get du equal to Cv dt. At constant volume, you should notice that on the right hand side of this equation it has no volume at all. The function is a function of temperature only. So as long as you start and you end at the same temperature as this case, the form of the equation remains very similar. You still get du equal to Cv dt. But please note that this Cv and that Cv may not have the same value. Okay, Cv is also state properties. So when you change the state properties, you change temperature, pressure, Cv will be changed as well. So heat capacity under ideal gas situation may not be the same value as heat capacity or generic heat capacity, even though the equation end up with the same form, but the value of the internal energy calculated under assumption of ideal gas may not be the same as the value calculated using generic equation. For enthalpy, generically, enthalpy can be written like that. Further derivative or further derivation, you end up with this equation. But you should notice that on the right hand side, it has you can not reduce this equation further under the constant volume condition. So you have to end up using this whole equation. For ideal gas, on the other hand, we start with enthalpy as a function of temperature only, and dH would equal to Cp dt always. Once again, on the right hand side, it has nothing to do with volume. It is function of temperature only. So it doesn't matter whether the process undergoes constant volume. Still, the enthalpy change depends on how much temperature is changed. So you end up with this equation. You can see that this equation is much simpler than the generic equation. So applying ideal gas assumption may give you a easier way to calculate the number, but it doesn't mean that the number is always true, as long as you need to consider the condition of your system. If the condition is applicable for ideal gas assumption, then the value should be relatively accurate. If you apply this to first law, the first law for general first law, or the first law for closed system, would be delta U equal to Q plus W. In this case, if we consider only for expansion work, then for constant volume process, the work is supposed to be 0. Taking delta U from this equation, when you integrate this equation, you get delta U. So therefore, heat would equal to integral of Cv dt. For generic case, if you apply delta U into the first law under the same assumption of no non-expansion work, and for constant volume process, work would equal to 0. You end up with similar form of the equation, but again, Cv here and Cv there might not be the same. So the heat that you calculated using generic equation might not be the same as the heat calculated under ideal gas assumption. For the second example, if the process undergoes constant pressure, these two equations, from under constant pressure, dP will become 0. So therefore, calculation of enthalpy change can be reduced into dH equal to Cp dt. But for du, you still have to use the original equation. For ideal gas, if you apply the constant pressure to these two equations, once again, as long as it depends on temperature change only, both internal energy change and enthalpy change depends on temperature change only. It doesn't matter whether pressure changes or not. So you still have the same equation. If you apply this one to the definition of enthalpy and take derivative of this equation under assumption or under the application of constant pressure, then derivative of PV should equal to PdV, because pressure itself is constant. You can take it out of the derivative. And from first law, du would equal to dq plus dw, where w can be written as minus pdv under assumption of the work is reversible. So if you plug this into this equation under assumption of constant pressure, then this minus pdv and this pdv would cancel out, and then you end up with heat equal to integral of Cp dt. Okay. The work itself, if you integrate the work, because pressure is constant, when you integrate PdV, you can take pressure out of the integration, leaving only integral of dV, which is V2 subtracted by V1. If I take V1 out of these parentheses, then you get V2 over V1 ratio subtracted by 1, which can be modified further using ideal gas relationship. From ideal gas relationship, PV over T1, P1 V1 over T1 equal to P2 V2 over P2 over V2, and pressure is constant, so therefore you end up with ratio of volume equal to ratio of temperature. If you apply this into here, then you can get this equation after you take temperature T1 out of this equation, out of the parentheses. Okay, and this group of the variables PV over T is essentially R according to ideal gas law. So you can get the work for constant pressure process under ideal gas assumption to be minus R delta T. The third case would be the process undergoes constant temperature change. In this case, these two dt would become 0, okay, leaving only these two terms. For ideal gas assumption, when dt becomes 0, you end up with du equal to 0 and dh equal to 0. So you can see that if you apply ideal gas assumption, as long as temperature does not change, both internal energy and enthalpy remains constant. It does not change at all as long as temperature does not change. But for generic fluid, there will be change, small change here and there. Okay. You can also analyze the equation, or you can end up with the same conclusion when you start with the fact that ideal gas, the internal energy of ideal gas depends on temperature only. So therefore, if temperature does not change, internal energy does not change either. So delta U for this process will become 0, and the same applies for enthalpy change. If you start by writing the first law, then when delta U becomes 0, Q would equal to minus W, and for reversible process, W is minus integral of P dV. Using ideal gas law, this pressure can be rewritten as RT over V. The reason that we need to convert pressure to this group because we need to describe this pressure as a function of volume before we do the integration. Okay, so if we change pressure to RT over V in this case, temperature is constant, can be taken out of the integration, leaving only 1 over V dV. Now you can do the integration to end up with RT logarithm of volume ratio. Once again, the volume ratio can be rewritten as a pressure ratio using ideal gas law, P1 V1 equal to P2 V2. Okay. So notice that heat calculated under this circumstance is totally different than what I wrote earlier, because now heat depends on path. Heat is the path properties. The last case would be adiabatic, reversible, and ideal gas. Okay, the term adiabatic means heat will become 0. In real life, there are couples of scenarios where heat becomes 0. The first one, the obvious one, is when the system is well insulated, and insulation here must be ideal insulation, so therefore heat from outside cannot go in and energy from inside cannot escape the system as heat. The second scenario where heat will be 0 is when temperature of system and temperature of surrounding are always the same, because temperature difference is the driving force for heat transfer. In this case, you have to notice that if as long as temperature on both sides of the system boundaries, or inside system and outside system, remains the same, there will be no heat. The third scenario is when heat cannot be transferred fast enough, or in other words, when the process takes place quickly, relatively quickly, so fast that heat has no time to transfer from the system to surrounding. In that case, you may also assume the system to be adiabatic. If the process is reversible, as stated here, the work here must be reversible work. So reversible work is minus PdV, while du is equal to Cv dt of the ideal gas. In this case, if you apply ideal gas law, changing pressure to RT over V, so that you end up with this equation. Now you see that in real life, this Cv is a function of temperature. Okay, we mentioned earlier that Cv of ideal gas is a function of temperature only. So you can move this Cv to the left hand side and do integration. But sometimes Cv is expressed in terms of polynomial. So sometimes it will be a little bit difficult to do the integration. So in general, I will say that Cv is a strong function of temperature. When you change temperature, Cv would change significantly. On the other hand, some people have noticed that the ratio between Cp and Cv changes with respect to temperature less extensively, less strongly. Okay, so we can say that this ratio is a weaker function of temperature compared to Cv itself. So we can make assumption that this ratio, which is called heat capacity ratio, is approximately constant, or it approximately unchanged with respect to change in temperature. Okay, so if we apply this assumption to our equation, what we like from this definition, if you apply the relationship between Cp and Cv under ideal gas assumption, Cp would equal to Cv plus R, and then rearrange this equation. If you divide this, you get 1 plus R over Cv, and move 1 into the left hand side, you end up with this relationship. Okay, and you should notice that R over Cv here is the same as R over Cv over there. So we can replace this term by gamma minus 1, ending up like this. Now since gamma, or heat capacity ratio, was assumed to be constant, you can do integration relatively easily. The left hand side, you end up with logarithm of the temperature ratio. On the right hand side, gamma will be taken to be constant, and then you integrate it, you get the logarithm of volume ratio. If you take exponential from both sides, you end up with this relationship. So T1 V1 to the power of gamma minus 1 equal to T2 V2 to the power of gamma minus 1. So therefore, you can also write generically that TV over gamma minus 1 is equal to constant. In order to find work for this case, you can start with this relationship in the box. Work would equal to du, and du equal to Cv dt. So the work itself can be obtained from integration of Cv dt. Or you can start from the definition of reversible work. Work would equal to minus Pdv and do the integration. In this case, if you apply ideal gas law, P would be RT over V, but you have to realize that this temperature is not constant. You cannot do integration right away. But you can convert this dV over V to be something like this. If you notice, these two terms highlighted in blue are essentially the same. So if you use this equation, rearrange this equation so that dV over V is equal to dt over t on this side, and you move this gamma minus 1 to the left hand side and plug it in here, you end up with this equation. And then now you can see that the right hand side here under the integration is a function of temperature only, because we take the heat capacity ratio gamma to be constant. If you take this one out of the integration, temperature here and temperature there would cancel out. You end up with the integral of dt, which is T2 subtracted by T1. Please notice that RT, if you apply the ideal gas law, RT is equal to PV. So we can either express the work as the RT2 subtracted by RT1 over gamma minus 1, or in terms of pressure and volume. So whether you should use this term or this term depends on the information you have in your hand. So from this equation, if you change temperature using ideal gas law again, you end up with volume here and volume there, which can be recombined. The constant R here can be moved to the right hand side. It remains constant, even doesn't matter when you add R into this right hand side, it's still constant. So for adiabatic reversible and ideal gas assumption, you can also rewrite the equation to be PV over gamma equal to constant. Now, this equation is used for this situation. But some people have seen this simple form of the equation and inspired to propose another equation. The difference between these two equations is this power. In this equation, the power is heat capacity ratio. It is applicable only for this situation. But generically, people have proposed that if we replace this power to another variable, delta, and then this generic equation can be called or can be used to describe any process. Okay, so this equation describes the process called polytropic process. What does it mean? Poly means a lot, right? It means that one single equation can describe so many situations. You have to keep in mind that this equation describes the relationship between pressure and volume along the way of the process. So essentially, this equation defines path of the process. How the process takes place depends on the value of the delta. Let me show you the plot here. When you see PV plot, you have to think of two things. First, PV behavior, just like I described in lecture 3a, is normally it has a dome here. Within the dome, there's a vapor-liquid equilibrium. On the right-hand side of the dome would be the behavior of vapor or gas, and on the left would be liquid. Okay, that's one aspect of PV diagram. The second thing that when you see PV chart or the plot between PV, you have to think about work, because work is normally obtained from integration of PDV. Essentially, it is area underneath the PV curve. So if I have a starting point, the initial point of the process, and the process undergoes this, complies with this equation. If delta is 0, when delta is 0, V here would be turned into 1. In other words, you end up with P equal to constant. So that means when you apply delta equal to 1, the equation describes the path of the process to be constant pressure. So the process is isobaric. When you start from the black dot initial point, you go along this red line. So this red line is described using this equation when delta is 0. Okay, so it defines the path of the process. If delta is 1, then you get PV equal to constant, or RT equal to constant, because PV can be converted to RT using ideal gas law. In other words, temperature is constant. It is isothermal condition. So from here, these two, you can see that the generic form of polytropic process can describe both depending on what the value of delta would be. Okay, so for delta equal to 1, under PV curve, you should get some sort like hyperbolic function, just like this pink line. Okay, so every state along this pink line follows this condition. So that's the meaning of what I said earlier, that this equation defines the path of the process. For delta equal to heat capacity ratio, then you end up with this equation that was previously mentioned for adiabatic reversible process. Okay, when you plot, you end up with this nonlinear function like that. Lastly, if you increase the value of delta approaching infinity, then you will see that doesn't matter how high the pressure would be, the multiplication of the products here remains constant when the volume does not change that much. Okay, because the power here is large number. In other words, this would become the function that does not depend much on volume. On extreme, when the delta approaching infinity, you end up with volume equal to constant. From the green line here, you will see again that if you find the area underneath the function, which would be the work, right? So let's start with the purple line here. The work for this process is area underneath the curve. But you can see that when the purple line turns into the green line, the area underneath becomes smaller and smaller, approaching zero eventually when it turns into vertical line, which is consistent with what we said earlier, that for constant volume process there is no expansion work, so W for this case would become 0. Okay, so if delta is not one of these 4 cases, then it would be general case and the path would be defined based on the given equation, and that would be applied to any change. And then it's not any change, it means that you can define the path using this simple equation, and that path is classified as polytropic process. Okay, so in this lecture I just give you introduction of equation of state by giving you the simplest one, the ideal gas equation. For the next 2 parts of lecture 3b, we will go further from ideal gas to more complicated equation that can describe behavior of generic fluid or generic gas much more accurately. So thank you for watching and see you in next clip.